This is the third in a series of videos about colligative properties. This one is going to be about vapor pressure lowering. So we talked about vapor pressure in the last chapter. So we talked about if you have a liquid and there are lots of different values for the kinetic energy of the particles in the liquid, some higher than others, and some of the highest kinetic energy particles have enough energy to vaporize into the gas phase. And if we were to put a lid on this container, make the walls a little bigger, there we go. If we put a lid on this container, then we can capture that pressure and we can measure the vapor pressure. And so that was when we just had one component in the liquid phase. But as you know, this chapter is about solutions where we have more than one component in the liquid phase. And as you may have guessed, there's going to be a change. So let's label this figure as pure water. Water as a pure solvent, the only thing in the container. And then let's draw a comparison of a different situation, also with the lid on. This one is going to be salt water, which is a solution of sodium chloride and water. Okay, so in our picture, we are going to have some liquid. There are going to be some sodium chloride ions in the solution. That's what these blue things are going to be. And then we're going to have our water molecules in red, like we did in the last picture. And in this case, as is indicated by the title, due to the additional intermolecular interactions with the new sodium chloride that's been added, there is still vaporization that occurs, but not as much. There isn't as much vaporization, so that vapor pressure above the solution is lower than it was above the pure solvent. So the pure solvent is greater than above the solution. So that's important, so let's write that out so we're very clear. So adding a solute increases the intermolecular interactions. And that decreases the vaporization. So it's all about those intermolecular forces. Okay, so this is the qualitative picture about the decrease in vaporization. But as you may have expected, there is a quantitative explanation involving a formula, and that is called Raoult's law. Okay, so here's how this formula works. So the partial pressure of component A in the gas phase is going to be equal to the mole fraction of A times the partial pressure of A in the pure solvent. So this little dot, the circle up here, this indicates the pure solvent. So this is a compound A by itself. And this mole fraction are always measured for the liquid phase. So let's make a note about that. So this is the partial pressure of the solvent vapor, solvent being the bigger volatile piece. This is the mole fraction of the solvent in the liquid phase. Very important. And then this one is the vapor pressure of the pure solvent. So this is actually one of the issues that's most difficult for me in general chemistry. So pay attention to the next couple of examples and try and understand how to use this formula and how to determine where to put the numbers where, the difference between partial pressure fraction and the mole fraction. So one area where you can easily become confused if you're trying to think about the pressure out of the total. So what we are not doing with this formula, we are not comparing the pressure of piece A to the pressure of the total. We're not talking about that fraction. What we are doing is we're comparing the pressure of A to the pressure when it's by itself. So the partial pressure of A in a mixture compared to partial pressure of A in a pure solvent. And I'll give you an example. And this example is going to be Rachel's algebra skills. So as you may have noticed, Rachel's algebra skills are much better when I am working by myself and I'm not on camera. And when I turn on the camera or when I'm with you together in person, suddenly I am unable to add and multiply numbers. And so this is just like this formula, and the way that my algebra skills would fit into this formula is that the mole fraction, which is me out of 34 students, multiplied by my algebra abilities in a pure solvent when I am by myself, would equal my algebra abilities when I am in the entire class. And so my algebra abilities by myself will be higher than my algebra abilities when I'm with all of you. My algebra skills do not depend on any of your algebra skills. They only depend on where I am. Am I by myself or am I in a mixture with other folks? Hopefully that helps. And if that didn't help, let's do an actual chemistry example. So this example says, find the vapor pressure above a solution, which was prepared by dissolving 35 grams of glycerin with this formula and 125 grams of water at this temperature. The vapor pressure of pure water is 17.5. So we know we're going to need Raoult's law. So let's just put that here. And I always include in liquid over here because I always forget to use it. So we need the partial pressure of A, which is going to be the water, the partial pressure of water by itself. We have that here. That's this guy. We are trying to find the vapor pressure of water above the solution, which is this. So what we need to find is the mole fraction. And we can see that we have the mass of the solute, the glycerin, and the mass of the solvent, which is the water. We just need to convert those to moles and find the fraction. So we can do that no problem. 125 grams of water. Then we need the molar mass of water. Oxygen is 16, hydrogen is 1. So this is going to be about 18.015 grams per mole. And that should give you 6.939 moles of water. And then let's do our other piece. Let's do our glycerin. 35 grams of glycerin, formula C3H8O3. Look up our formula. Carbon is 12, oxygen 16, hydrogen 1. Total molar mass should be 92.094 grams per mole. And we should end up with 0.380 moles of glycerin. Okay, let's refocus. We're trying to find mole fraction, and we're mostly interested in the mole fraction of the water. And so for the mole fraction, we need to have the moles of the water and the moles of the total. So if we add these two together, we can get total moles. You should get 7.319 moles total. Okay, so now we can take that number and we can plug and chug. So our mole fraction is moles of water, 6.939, over total moles, 7.319. And then we can plug in our pure vapor pressure of water at this temperature, 17.5 torr. And that gives us 16.6 torr vapor pressure of water in a mixture. So let's do the bullshit test to make sure this makes sense. So here, when water was by itself, it had a vapor pressure of 17.5 torr. And so we expect when water is mixed in with something else that its vapor pressure should be lower. And we can see that yes, 16.6 torr is a lower amount. It's always important to check and make sure you have a reasonable looking answer before you leave it and turn it in. Let's look a little bit closer and just bring that back around to the definition of colligative properties to make sure we're all on the same page. So to review, the pressure of pure water when it was by itself was 17.5 torr. And if we subtract the pressure of water when it was in a mixture, so this was 6.939 moles of water, and then we mixed it with 0.380 moles of glycerin. So when the water was mixed with that glycerin, it had a partial pressure of 16.6. And if we look at how much the vapor pressure lowered, it's going to be negative 0.9 torr. That's our change in vapor pressure. And so remember that this is going to be true whether it's glycerin or whether it's anything else added to the solution, because this is a colligative property. So colligative properties don't depend on the substance identity. Ooh, we are a little bit off the camera there. Sorry, guys. There we are. Colligative properties don't depend on the identity. So I could have this many moles of glycerin, as we did in the problem. I could have this many moles of glucose. I could have this many moles of sodium chloride. No matter what compound I have, I'm always going to end up with a vapor pressure lowering of negative 0.9 torr. So as long as the number of moles is the same and we have the same mole fraction, the amount that the vapor pressure will be lowered for water will always be the same. In the next video, we will use our new knowledge about vapor pressure lowering to talk about distillation and how that important industrial process works.